Picture yourself standing at the shore of an ancient ocean, waves lapping at your feet as you gaze toward the horizon. Where does the water end? What lies beyond that line where sky meets sea? This fundamental human question, this burning need to know where things stop and what comes next, has driven our species to explore every corner of our world and beyond. But perhaps nowhere is this question more profound, more mind-bending, than when we turn our eyes to the cosmos itself and ask, where does the universe end, and what exists outside its edge? Long before telescopes pierced the night sky, long before we understood that stars were distant suns, or that galaxies spiraled through space, ancient civilizations grappled with the ultimate boundary question. They looked up at the star-studded dome above and wondered what lay beyond. The Babylonians, master astronomers of their time, imagined the heavens as a great solid vault, a crystalline sphere that enclosed the entire world. To them, the stars were holes poked through this celestial ceiling, allowing divine light to shine through from whatever realm existed beyond. The ancient Egyptians painted their cosmology in tombs and temples, depicting the sky as the body of the goddess Nut, stretched across the heavens like a protective canopy. Her star-covered skin formed the boundary between the world of the living and the mysterious afterlife beyond. Each night, she would swallow the sun, only to give birth to it again at dawn. Their universe had clear edges, defined by divine anatomy and eternal cycles. Hindu cosmology described the universe as contained within a cosmic egg, the Brahmanda, floating in an infinite ocean of potential. Beyond this egg lay other universes, other realities, stretching without end. Even in this ancient vision, the question persisted: what exists in that vast ocean between the cosmic eggs? The Rig Veda, composed over 3,000 years ago, contains perhaps humanity's earliest written contemplation of cosmic boundaries. Who knows from whence this creation arose? Whether he created it or not, he who surveys it from the highest heaven, he alone knows, or perhaps he knows not. The Greeks, with their love of geometry and logic, constructed cosmos models that satisfied both observation and philosophy. Aristotle proposed a universe of nested crystalline spheres, each carrying a planet or star in perfect circular motion around the Earth. The outermost sphere, the one containing the fixed stars, marked the absolute boundary of existence. Beyond it, nothing at all. Not empty space, not darkness, but literally nothing. The very concept of beyond became meaningless at the edge of Aristotle's universe, but it was the human mind's relationship with boundaries that proved most fascinating. We are creatures of edges and borders. Every day we navigate the boundaries between rooms, between properties, between nations. We define ourselves by what we are and what we are not, by where we end and the world begins. This psychological need for demarcation runs so deep that we unconsciously apply it to everything we encounter. A forest must have edges where it meets meadows or cities. An ocean must have shores where it touches land. And surely, logically, the universe itself must have some kind of boundary, some ultimate edge where existence stops and something else begins. Medieval European scholars inherited Aristotelian cosmology and wrapped it in Christian theology. They imagined the starry sphere as the floor of heaven, with God and the angels dwelling in the empyrean beyond. The great Italian poet Dante, in his Divine Comedy, described ascending through the celestial spheres until reaching the primum mobile, the outermost sphere whose rotation powered all the others. Beyond even this lay the empyrean, pure light and love, the true dwelling place of the divine. Here was a universe with a definitive edge and a clear answer to what lay beyond: God's infinite perfection. These ancient and medieval worldviews shared common themes. They provided comfort through comprehensibility. The universe had walls, boundaries, edges that human minds could grasp. There was an inside where we lived, and an outside where gods, spirits, or simply nothingness resided. The cosmology might be vast by human standards, but it remained fundamentally finite and bounded, like the villages and kingdoms that comprise their daily experience. The Renaissance shattered these comfortable boundaries. Nicholas Copernicus moved the Earth from the center of creation to just another planet orbiting the Sun. Suddenly, the crystalline spheres carrying the planets became unnecessary. Giordano Bruno went further, proposing that the stars were distant suns, each potentially surrounded by their own planets. If this were true, then the starry sphere wasn't a boundary at all, but merely the limit of human vision. Beyond the visible stars lay more stars, and beyond those, still more, perhaps extending infinitely in all directions. Bruno paid for this insight with his life, burned at the stake in 1600 for heresy, but his ideas proved prophetic. Galileo's telescope, pointed skyward in 1609, revealed what the naked eye could never see. The Milky Way was not a faint cloud, but countless distant stars. The moon had mountains and craters, making it a world like Earth rather than a perfect celestial object. Jupiter had its own moons, proving that not everything orbited our planet. Each observation pushed the boundaries of the known universe further outward. As telescopes improved through the 17th and 18th centuries, astronomers discovered that the universe was far larger than anyone had imagined. William Herschel mapped the structure of the Milky Way galaxy, showing that our solar system was just one tiny part of a vast stellar island. He also discovered that some of the fuzzy patches visible in telescopes were actually other island universes, entire galaxies beyond our own. The cosmic boundary kept receding, always staying just beyond the reach of our most powerful instruments. The 19th century brought new tools and new mysteries. Spectroscopy allowed astronomers to analyze the light from distant stars and nebulae, revealing their chemical composition and motion. Photography enabled long exposures that captured faint objects invisible to the eye. The universe revealed layer upon layer of previously hidden structure. Nebulae that had appeared as simple clouds resolved into complex spiral and elliptical shapes. Star clusters contained thousands or millions of individual suns. And still, the question persisted: where does it all end? By 1900, astronomy had expanded human perception far beyond anything the ancients could have imagined. The observable universe stretched millions of light years in every direction, filled with countless stars organized into vast galactic systems. Yet the fundamental question remained as compelling as ever. The human need for edges, for boundaries, for a comprehensible limit to existence demanded an answer. If the universe was this large, how much larger could it be? Did it go on forever? Or was there some ultimate cosmic shoreline where space and time themselves came to an end? The ancient mythologies had provided clear, if wrong, answers to these questions. The universe was contained within a dome, a vault, an egg. Beyond lay the realm of gods or the realm of nothingness. These answers satisfied the human psychological need for boundaries, even as they failed to match observational reality. Modern astronomy had stripped away these comfortable certainties without providing adequate replacements. The universe appeared larger than human minds could readily comprehend, yet surely it must have limits. Surely there must be some edge, some boundary, some ultimate shore against which the cosmic ocean lapped. As the 20th century dawned, this ancient question was about to transform from mythology and philosophy into rigorous science. New discoveries in physics would reveal that the universe was not only larger than we had imagined, but stranger. The very concepts of space and time would be revolutionized, and with them, our understanding of what it might mean for the universe to have an edge or to exist outside the cosmic boundary. The human need for edges was about to collide with the reality of modern cosmology. The comfortable certainties of bounded space would give way to mind-bending possibilities, universes that expanded, curved back on themselves, or extended infinitely in all directions. The ancient question, what lies beyond the edge, would become more profound and more puzzling than any mythmaker or philosopher had ever imagined. Science was about to inherit humanity's oldest cosmic mystery and transform it into something far stranger than fiction. The year was 1929, and Edwin Hubble stood before the most powerful telescope on Earth, the 100-inch Hooker telescope atop Mount Wilson in California. What he was about to announce would shatter every assumption about the nature of cosmic space itself. The universe, he declared, was not the static, eternal structure that philosophers and scientists had imagined for millennia. Instead, it was growing, stretching, expanding in all directions at once. Hubble's discovery began with light itself, specifically with the colors hidden within starlight. When astronomers passed the light from distant galaxies through prisms, they found familiar patterns, the same spectral lines produced by hydrogen, helium, and other elements in laboratory experiments on Earth. But something was wrong. These lines weren't appearing where they should. Instead, they were shifted toward the red end of the spectrum, stretched to longer wavelengths, as if the light itself had been pulled like taffy during its journey across space. This redshift phenomenon had been noticed before, but Hubble did something revolutionary. He measured the distances to these galaxies using a special type of star called a Cepheid variable, stars that pulse with predictable brightness patterns. The further away a galaxy was, he discovered, the more its light was redshifted. This wasn't random. It was a perfect mathematical relationship. Distance and redshift increased together in lockstep across the cosmos. The implications hit the scientific community like a thunderbolt. If galaxies were moving away from us, and more distant galaxies were moving away faster, then the entire universe was expanding. Not expanding into something, not growing larger within some pre-existing container, but expanding in the most fundamental sense possible. Space itself was stretching, carrying galaxies along like raisins in rising bread dough. Picture a balloon with dots marked on its surface. As you inflate the balloon, every dot moves away from every other dot. The dots themselves don't move across the balloon's surface, rather the surface itself expands, increasing the distance between all points simultaneously. This was the revolutionary insight. Galaxies weren't flying through space away from some cosmic explosion site. Instead, new space was continuously being created between them. This discovery demolished the comfortable notion of a static cosmic architecture. The universe wasn't a fixed stage upon which celestial dramas played out over eternal time. It was dynamic, evolving, changing moment by moment as space itself stretched. Every cubic centimeter of seemingly empty void between galaxies was expanding, creating more cubic centimeters of void, which in turn expanded to create still more. The mathematics of this expansion revealed something even more startling. If the universe was growing now, then logically it must have been smaller in the past. Wind the cosmic clock backward, and the galaxies draw closer together. Keep rewinding, and the entire observable universe shrinks down to the size of a galaxy, then a solar system, then a planet. Continue this backward journey, and everything we can see today was once compressed into a volume smaller than an atom. This mathematical inevitability led to the most audacious scientific theory ever proposed: the Big Bang. Roughly 13.8 billion years ago, our entire observable universe emerged from a state of unimaginable density and temperature. Not an explosion in space, but an explosion of space itself, the violent birth of the very fabric of reality we inhabit today. But Hubble's expanding universe created new puzzles about cosmic boundaries. In the old static model, the edge question was straightforward, even if unanswerable. The universe was some fixed size, finite or infinite, and that was that. But an expanding universe introduced temporal complexity. How big was the universe now? How big would it be tomorrow? Did expansion imply that the universe had definite boundaries that were moving outward, like the surface of an inflating balloon? The answer proved more subtle than anyone expected. Einstein's theory of general relativity, published in 1915, had already suggested that space and time were woven together into a four-dimensional fabric called spacetime. Mass and energy curved this fabric, creating the phenomenon we experience as gravity. But the expanding universe revealed another property of spacetime. It could stretch. When we say space is expanding, we mean something very specific. The distance between widely separated objects increases over time, not because the objects are moving through space, but because space itself is growing. A photon of light traveling from a distant galaxy doesn't journey through static space to reach us. Instead, it surfs the expanding space-time, its wavelength stretched by the cosmic growth occurring during its billion-year journey. This expansion happens everywhere simultaneously. In the time it takes you to read this sentence, the space between distant galaxy clusters has grown by thousands of kilometers. Yet you don't notice any stretching in your immediate environment because gravitational forces hold local structures together. The expansion only becomes apparent on scales much larger than individual galaxies, where gravity's grip weakens and the underlying stretching of space takes over. The cosmic expansion rate, known as the Hubble constant, tells us how fast space is stretching. Current measurements indicate that for every megaparsec of distance, roughly 3.2 million light-years, space expands at about 70 kilometers per second. This means that two galaxies separated by 10 megaparsecs are receding from each other at 700 kilometers per second, not because they're racing through space at that speed, but because the space between them is expanding at that rate. This expansion creates a horizon, a boundary beyond which we cannot see. Light from the most distant observable galaxies has been traveling toward us since shortly after the Big Bang, but the expansion of space has stretched its wavelength into the microwave region of the electromagnetic spectrum. This cosmic microwave background radiation represents the furthest we can see, the edge of our observable universe at roughly 46 billion light-years away. But here's where the edge question becomes truly mind-bending. The observable universe has this boundary, this horizon beyond which we cannot see. Yet the expansion itself provides no evidence for an edge to the universe as a whole. Every measurement suggests that space continues beyond our horizon, filled with more galaxies, more stars, more of the same cosmic architecture we observe locally. Think of standing in a vast wheat field. Your horizon limits how far you can see, but the field continues beyond that visual boundary. Similarly, our cosmic horizon limits our view, but space itself appears to continue indefinitely beyond what we can observe. The expanding universe doesn't require an edge any more than the surface of an expanding balloon requires an edge. The expansion also resolves some ancient paradoxes. If the universe were infinite and static, as some had proposed, then the night sky should be blazing with starlight from infinitely many stars in every direction. But in an expanding universe that began a finite time ago, we can only see light from stars within our cosmic horizon. The darkness between stars isn't a mystery. It's evidence of cosmic expansion and finite age. Yet expansion introduces new paradoxes. If space is stretching everywhere, why don't we notice it locally? Why don't our measuring rods expand along with space? The answer lies in the binding forces that hold matter together. Electromagnetic forces keep atoms intact. Nuclear forces bind protons and neutrons. Gravitational forces bind planets to stars and stars to galaxies. These forces resist the expansion, creating stable structures in an otherwise stretching cosmos. The expansion of space also means that distant galaxies appear to be receding faster than the speed of light. This seems to violate Einstein's cosmic speed limit, but it doesn't. The galaxies aren't moving through space faster than light. Rather, the space between us and them is expanding so rapidly that the cumulative effect exceeds light speed. This is perfectly allowed by relativity, which only prohibits objects from moving through space faster than light. As we peer deeper into space, we're also looking further back in time. Light from distant galaxies shows us how they appeared billions of years ago, when the universe was younger and smaller. The most distant galaxies we can observe appear as they were when cosmic expansion had only recently begun, when the universe was a fraction of its current size. This time delay effect means that the edge of our observable universe is not just a spatial boundary, but a temporal one as well. We're seeing the universe as it was nearly 14 billion years ago, shortly after the cosmic dark ages ended and the first stars began to shine. Beyond this temporal horizon lies not empty space, but earlier epochs, times when the universe was too hot and dense for normal matter to exist. The expanding universe transformed the edge question from a simple spatial puzzle into a complex interplay of space, time, and cosmic evolution. The comfortable notion of a universe with clear boundaries gave way to a dynamic cosmos where horizons shift, space stretches, and the very meaning of edge becomes ambiguous. But if the universe is expanding, what is it expanding into? This question haunts our imagination because it seems so natural, so obvious. When a balloon expands, it grows larger within the room that contains it. When a city expands, it spreads into the surrounding countryside. Surely the expanding universe must be growing into some larger space, some cosmic container that existed before the expansion began. The answer challenges our deepest intuitions about space itself. The universe isn't expanding into anything because space is not a container. Space is the thing that's expanding. There is no outside space because space defines the very meaning of location and distance. Asking what the universe is expanding into is like asking what's north of the North Pole. The question itself reveals a misunderstanding of the fundamental nature of cosmic space. This realization brings us face to face with the ultimate boundary question. If space itself is expanding, and if there's no container into which it expands, then what does it mean to ask what lies beyond the edge? The expanding universe suggests that the edge question itself might be based on faulty assumptions about the nature of space, time, and existence itself. Imagine you're a lighthouse keeper on a foggy night, your beacon cutting through the darkness for exactly 10 miles before the light fades into invisibility. Beyond that 10-mile circle lies more ocean, more waves, more ships potentially sailing in the darkness, but they remain forever hidden from your sight. The ocean doesn't end at 10 miles, your vision does. This is precisely the situation we face when we gaze into the cosmos. We have a horizon, a boundary to our sight, but this boundary tells us nothing about whether the universe itself has edges. The cosmic horizon emerges from a fundamental speed limit woven into the fabric of reality itself. Light, the fastest thing in the universe, travels at exactly 299,792,458 meters per second through empty space. This isn't just fast, it's the ultimate speed limit for any information or influence to travel from one point to another. Even if alien civilizations, a billion light years away, built the most powerful radio transmitters imaginable, their signals could never reach us faster than light itself. This speed limit creates an inevitable boundary, light from the most distant galaxies has been traveling toward us since shortly after the Big Bang, roughly 13.8 billion years ago. You might expect this means we can see galaxies up to 13.8 billion light-years away, but cosmic expansion complicates this simple calculation. While light was journeying toward us, space itself was stretching, carrying those distant galaxies even further away. Consider a photon that began its journey when the universe was very young, perhaps only a few 100 million years old. At that time, the galaxy that emitted it was much closer to the location where our Milky Way would eventually form. But as this photon traveled through space for billions of years, cosmic expansion continuously stretched the distance between its source and its destination. By the time the photon finally reaches our telescopes today, its source galaxy has been carried by expansion to a distance of roughly 46 billion light-years. This creates what astronomers call the particle horizon, the boundary of our observable universe. It's not a physical wall or barrier, but rather the furthest distance from which light has had time to reach us since the Big Bang began. Everything within this sphere, centered on Earth and extending 46 billion light-years in every direction, represents the totality of what we can potentially observe. Beyond this horizon lies the unobservable universe, regions of space that exist but remain forever hidden from our view. The observable universe contains staggering numbers. Within our cosmic horizon lie roughly 2 trillion galaxies, each containing hundreds of billions of stars. If you could count 1 star per second, it would take you longer than the current age of the universe to count just the stars in a single large galaxy. Yet all of this represents only the tiny fraction of the universe that happens to lie within our observational reach. But the cosmic horizon is not static. Every second, light from slightly more distant regions reaches us for the first time, expanding our observable universe by 300,000 kilometers in all directions. Objects that were previously beyond our horizon yesterday cross into observability today. In a sense, we're constantly discovering new territory as the cosmic horizon expands outward at the speed of light. However, cosmic expansion works against this growth in a crucial way. While our horizon expands, carrying distant galaxies away from us so rapidly that many of them will eventually disappear from our view entirely. Galaxies currently visible at the edge of our observable universe are already receding so fast that any light they emit today will never reach us. We're seeing them as they were billions of years ago, but their present-day light is racing toward us through expanding space that stretches faster than the light can travel. This creates a profound cosmic loneliness. Trillions of galaxies that we can see today will fade from view over the next 100 billion years. Their light redshifted beyond detection as they cross what astronomers call the event horizon. Future civilizations, if they exist, will inhabit a much darker universe, surrounded by only the few thousand galaxies in our local gravitationally bound cluster. They will see a cosmos that appears static and finite, unaware that trillions of galaxies once filled their night sky. The cosmic microwave background provides our deepest view into the past, representing the moment when the universe first became transparent to light. Before this epoch, roughly 380,000 years after the Big Bang, the cosmos was so hot that electrons couldn't bind to atomic nuclei. Free electrons scattered photons continuously, making the universe opaque like the interior of a star. When temperatures finally dropped enough for atoms to form, this cosmic fog cleared, and light could travel freely for the first time. This first light still fills the universe today, stretched by cosmic expansion from its original visible wavelengths into microwave radiation. We can detect this ancient glow in every direction, a perfect sphere of radiation that represents the surface of last scattering, the moment when the universe became transparent. This forms our ultimate observational boundary, beyond which no light from earlier epochs can reach us. The cosmic microwave background reveals the universe at its most homogeneous epoch, when matter was distributed with near-perfect uniformity in all directions. Tiny fluctuations in this ancient light, variations in temperature of only a few parts per million, represent the seeds from which all cosmic structure eventually grew. Galaxies, stars, and planets all trace their origins to these minute irregularities in the primordial cosmos. Temperature variations in this ancient radiation follow patterns that reveal the geometry of space itself. Just as the curvature of Earth's surface affects how triangles drawn on its surface behave, the curvature of cosmic space affects how hot and cold spots are distributed across the microwave background. Current measurements indicate that space is remarkably flat, at least within our observable region, suggesting that the universe might extend far beyond what we can see. Our horizon also creates an observational selection effect. We can only study physics within our cosmic boundary, which represents conditions in our local region of what might be a much larger and more diverse universe. The physical laws we've discovered, the fundamental constants we've measured, the cosmic history we've reconstructed, all apply specifically to our observable patch. Whether these same properties extend throughout the larger universe remains unknown. Different types of horizons layer upon each other in cosmic space. The particle horizon marks the boundary of regions from which light has reached us. The Hubble horizon indicates the distance at which cosmic expansion makes objects recede at the speed of light. The event horizon delimits regions whose future light will eventually reach us. Each horizon reveals different aspects of cosmic structure and evolution. The cosmic horizon also demonstrates how observation shapes reality in astronomy. Unlike laboratory physics, where we can manipulate experimental conditions, cosmology relies entirely on passive observation of distant phenomena. We cannot visit other galaxies, cannot sample the cosmic microwave background directly, cannot conduct controlled experiments on cosmic expansion. The horizon defines not just what we can see, but the fundamental limits of what we can ever know about cosmic reality. Peering toward our cosmic horizon is like reading the universe's autobiography, written in the language of light itself. Every photon carries information about the conditions that existed when and where it was emitted. Ancient light tells us about stellar nucleosynthesis in the first generation of stars. Slightly less ancient light reveals how galaxies assembled from dark matter scaffolding. Recent light shows us cosmic acceleration and dark energy's influence on expansion. The horizon boundary shifts continuously as new light arrives and cosmic expansion evolves. In regions where expansion is accelerating, some horizons actually shrink over time, limiting future observational possibilities. In other cosmic epochs, when expansion was decelerating, horizons grew more rapidly than they do today. The boundary between observable and unobservable is thus dynamic, evolving with cosmic history itself. Perhaps most remarkably, our cosmic horizon exists not because the universe has boundaries, but because light has a finite speed and the cosmos has a finite age. In an infinitely old universe with infinite extent, no horizon would exist at all. Every point would be observable given sufficient time. The horizon emerges from the interplay between cosmic expansion, light speed limits, and the Big Bang's temporal boundary. This raises profound questions about the relationship between observation and existence. Does the unobservable universe actually exist if we can never detect it? Philosophy aside, physics strongly suggests that space continues beyond our horizon, filled with the same types of matter and energy we observe locally. The laws of physics provide no mechanism for the universe to suddenly terminate at our observational boundary. The cosmic horizon thus represents humanity's ultimate geographical frontier. We have explored every continent on Earth, sent spacecraft throughout the solar system, detected planets around other stars, and mapped the large-scale structure of the observable universe. But the horizon remains forever beyond our reach, not because we lack sufficiently advanced technology, but because the fundamental structure of space-time itself limits how far we can see. Yet this boundary is not a wall or edge in any physical sense. It's a limitation of observation, not a termination of existence. Like our lighthouse keeper, whose beacon illuminates only 10 miles of ocean, we see only a finite region of what appears to be a much larger cosmic sea. The horizon marks the edge of knowledge, not the edge of reality itself. Standing at the edge of a vast desert, you face an impossible question. Does the sand extend forever in all directions, stretching across infinite dunes under an endless sky? Or does it eventually terminate at some distant boundary, perhaps where mountains rise or oceans begin? This same fundamental question confronts us when we contemplate cosmic space itself. Is the universe infinite, containing endless volumes of space filled with countless galaxies? Or is it finite, bounded in some way that our minds can barely comprehend? Einstein's general relativity, published in 1915, revolutionized our understanding of space and time by revealing that they form a unified fabric that can curve, stretch, and bend. This geometric insight provides three distinct possibilities for the overall shape of cosmic space, each with profound implications for whether the universe has boundaries or extends infinitely. Picture the surface of a sphere, like Earth itself. This surface has finite area, yet no boundaries or edges. You can travel in any direction across Earth's surface and never reach a point where the surface ends. If you continue walking straight in any direction, you'll eventually return to your starting point, having circumnavigated the globe. Mathematicians call this a closed geometry, and it represents one possibility for the shape of our three-dimensional cosmic space. In a closed universe, space curves back on itself, just as Earth's surface curves. The total volume would be finite, yet there would be no edges or boundaries anywhere. A spaceship traveling in any direction through a closed universe would eventually return to its starting point, just as Magellan's expedition circumnavigated Earth. This creates the bizarre possibility of a universe that is both finite and boundaryless, like a three-dimensional version of Earth's surface. The second possibility resembles a saddle shape, where the surface curves in opposite directions. Imagine a mountain pass where the ground curves upward toward the peaks, but downward toward the valley. This hyperbolic or open geometry extends infinitely in all directions. In an open universe, space would curve in a way that makes it infinite in extent, with no boundaries or edges, but also no possibility of returning to your starting point, no matter how far you travel. The third possibility is perfectly flat space, the familiar Euclidean geometry we learn in school. In flat space, parallel lines never meet. Triangles have angles that sum to exactly 180 degrees, and the circumference of a circle equals pi times its diameter. Flat space can be either finite or infinite, depending on whether it wraps around on itself like the surface of a cylinder or extends forever like an infinite plane. These three geometries represent the only possibilities allowed by Einstein's equations when applied to a homogeneous universe. The actual geometry of our cosmos depends on the total amount of matter and energy it contains. Too much matter and energy and gravity curves space into a closed sphere. Too little, and space curves into an infinite saddle. Just the right amount, and space remains perfectly flat. For decades, astronomers struggled to measure cosmic geometry with sufficient precision to determine which of these three possibilities describes our universe. The task required mapping the cosmic microwave background with extraordinary accuracy, measuring the brightness of distant supernovae, and surveying the distribution of galaxies across billions of light-years of space. The results, accumulated over the past 2 decades, point toward a startling conclusion. Our universe appears to be geometrically flat, at least within our observable region, to a precision of about 1%. This flatness extends across the entire 46 billion light-year radius of our cosmic horizon, suggesting that if space has any curvature at all, it must be incredibly subtle. But geometric flatness doesn't resolve the infinite versus finite question. A flat universe could be infinite, extending forever in all directions like an endless plane. Alternatively, it could be finite but boundaryless, wrapping around on itself like the surface of a torus or more complex topological shapes. These finite flat spaces would have no edges, yet contain only a limited volume. If the universe is infinite, then it contains infinite amounts of matter and energy distributed across infinite space. Every possible arrangement of atoms would occur not just once, but infinitely many times across the cosmic expanse. Somewhere in an infinite universe, there would be perfect copies of Earth, exact duplicates of every person who has ever lived, and infinite variations on every possible theme. This leads to the paradox of infinite repetition. In an infinite universe with finite types of elementary particles, the number of possible arrangements within any given volume is large, but finite. An infinite universe would therefore contain infinite copies of every possible arrangement, including infinite copies of you reading these words in the circumstances identical to your current situation. The mathematics of infinity creates even stranger possibilities. An infinite universe would contain regions where the laws of physics appear to break down simply due to statistical fluctuations. In vast enough expanses of space and time, random quantum events could spontaneously assemble complex structures, including brains with false memories of entire lifetimes that never actually occurred. These Boltzmann brains, named after the Austrian physicist Ludwig Boltzmann, represent a profound challenge to our understanding of cosmic reality. If the universe is infinite and eternal, then such randomly assembled conscious entities would vastly outnumber biological brains like ours. Statistical arguments would suggest that you are more likely to be a Boltzmann brain with false memories than a biological entity with genuine experiences. A finite universe avoids these paradoxes by limiting the total amount of space and matter. In a finite cosmos, there would be only one of everything, including only one version of you. The arrangements of matter would be vast, but not infinite, eliminating the problems of infinite repetition and statistical dominance by random fluctuations. Current observations cannot distinguish between infinite and finite flat universes. If our cosmos wraps around on itself, the circumnavigation distance would have to be larger than our observable horizon for us to detect the topology. We might live in a finite universe whose boundaries lie beyond our current observational reach, making it appear infinite from our limited perspective. Some theoretical approaches suggest that the universe must be infinite. Cosmic inflation, the period of rapid expansion believed to have occurred in the universe's first fraction of a second, could have stretched space to infinite extent. If inflation lasted long enough, or occurred with sufficient intensity, even an initially finite region could have been expanded to infinite size. Other theories propose that the universe began with infinite extent and has remained infinite throughout its history. In these models, the Big Bang represents the beginning of time, but not the beginning of space. Infinite space would have existed from the very first moment, filled with the energy that drives cosmic expansion. The question of cosmic finiteness or infinity connects to deep issues in the foundations of physics. Quantum mechanics suggests that space and time might not be continuous, but rather composed of discrete units at the smallest scales. If space consists of finite-sized pixels, like a cosmic computer screen, then even an apparently infinite universe might contain only finite information. String theory and other approaches to quantum gravity propose that space has additional dimensions beyond the three we directly experience. These extra dimensions might be finite even if the familiar three dimensions extend infinitely. The universe could be infinite in some directions, but finite in others, creating hybrid geometries that combine aspects of both possibilities. Observational cosmology continues to probe the geometry and topology of space with increasing precision. Future surveys will map the cosmic microwave background with unprecedented detail, potentially revealing subtle signatures of finite topology. Gravitational wave detectors might eventually detect echoes from cosmic events, providing new ways to probe the large-scale structure of space. The cosmic microwave background already provides tantalizing hints about cosmic geometry. The patterns of hot and cold spots encode information about the curvature of space when the universe was only 380,000 years old. These patterns appear consistent with flat geometry across our entire observable region, but they cannot reveal whether space extends infinitely beyond our horizon. Dark energy, the mysterious force driving cosmic acceleration, might also constrain cosmic geometry. If dark energy has been constant throughout cosmic history, it favors infinite flat universes. But if dark energy evolved over time or varies from place to place, it could support finite cosmologies with complex topologies. The philosophical implications of infinite versus finite space are profound. An infinite universe contains everything that could possibly exist, making our local region just one of infinitely many similar domains. A finite universe makes our cosmic region special, perhaps unique, with no exact copies existing anywhere else. If the universe is infinite, then questions about what lies beyond its boundaries become meaningless. There are no boundaries to transcend in infinite space. But if the universe is finite, even without edges, then we might wonder what mathematical or physical framework contains the cosmic volume, even if that framework isn't spatial in any familiar sense. The flatness of space also has implications for cosmic evolution. In closed universes, expansion eventually reverses, leading to a big crunch where all matter collapses back together. Open universes expand forever, growing colder and more dilute until stars burn out and black holes evaporate. Flat universes balance on the knife edge between these extremes, expanding forever but at an ever-decreasing rate. Current observations suggest our universe is not only flat but also accelerating, driven by dark energy that counteracts gravitational attraction on cosmic scales. This acceleration pushes us further into the regime of eternal expansion, regardless of whether space is finite or infinite in extent. The question of cosmic finiteness versus infinity remains one of the deepest unsolved problems in cosmology. Our observations reveal a universe that appears infinite from our limited perspective. Yet the fundamental nature of space and time, at the largest scales, remains mysterious. Whether we inhabit a finite cosmos that wraps around on itself, or an infinite expanse that extends forever beyond our horizon, may represent the ultimate boundary question, one that challenges both our observational capabilities and our conceptual understanding of existence itself. Imagine standing on a mountaintop on a perfectly clear day, gazing across endless forests that stretch to the horizon in every direction. You know that beyond your line of sight, the forest continues, filled with the same trees, streams, and wildlife you can observe nearby. The horizon doesn't mark where the forest ends. It simply marks the limit of your vision. This analogy captures one of the most profound insights in modern cosmology. Beyond the boundary of our observable universe lies more universe, more galaxies, more cosmic structure extending far beyond what we can ever hope to see. The unobservable universe represents perhaps the largest arena of existence we can never directly explore. While our cosmic horizon encompasses roughly 2 trillion galaxies, Within a sphere 46 billion light-years in radius, this represents only the tiny fraction of cosmic space that happens to lie within our observational reach. Beyond this boundary stretches additional space, filled with matter and energy, governed by the same physical laws that operate within our observable domain. Every piece of evidence suggests that the space beyond our horizon continues the patterns we observe locally. Galaxies should be distributed with the same statistical properties. Stars should be forming and dying according to the same nuclear physics, and cosmic expansion should be stretching space at the same rate we measure nearby. The fundamental forces of nature, electromagnetic, gravitational, strong nuclear and weak nuclear, should operate identically in these unreachable regions. This cosmic democracy principle holds profound implications. If the laws of physics are truly universal, then the unobservable universe contains stellar nurseries where new stars are being born from collapsing gas clouds, mature solar systems where planets orbit their parent stars, and dying massive stars that explode as supernovae, scattering heavy elements into the cosmic medium. All the cosmic processes we study through our telescopes are presumably playing out on vastly larger scales beyond our observational reach. The cosmic microwave background provides our strongest evidence for the uniformity of the larger universe. This ancient radiation, emitted when the cosmos first became transparent, shows remarkably uniform temperature in all directions, varying by only a few parts per million across the entire sky. Such uniformity suggests that the physical conditions in our observable region are representative of much larger volumes of space. Cosmic inflation theory predicts that the unobservable universe should be vastly larger than what we can see. During the first tiny fraction of a second after the Big Bang, space expanded exponentially, stretching microscopic quantum fluctuations to astronomical scales. If inflation occurred as theorists propose, then our entire observable universe represents just one small patch of a much larger inflated region, perhaps containing 10 to the power 23 times more volume than we can observe. Within this vast, unobservable expanse, statistical arguments suggest remarkable possibilities. If space extends far enough beyond our horizon, then somewhere in the cosmic deep, there should be regions where matter arranged itself into configurations identical to what we see locally. The same random processes that produced our particular cosmic neighborhood would, given sufficient space and time, reproduce similar arrangements elsewhere. Consider the formation of galaxies from primordial density fluctuations. Gravity amplified tiny irregularities in the early universe, causing matter to collapse into the cosmic web of filaments and voids we observe today. In an unobservable universe thousands of times larger than our horizon, these same gravitational processes would have produced cosmic structures statistically similar to our local cosmic neighborhood, including regions where galaxies arrange themselves in patterns nearly identical to what we see around us. The implications become even more startling when we consider planetary systems. If the unobservable universe is sufficiently vast, then somewhere beyond our cosmic horizon, stellar formation and planetary assembly should have produced solar systems remarkably similar to our own. The same physical processes that led to Earth's formation from a disk of dust and gas around the young sun would operate identically in these distant domains. This raises the possibility of cosmic twins, regions of the unobservable universe where matter evolved along paths nearly parallel to our own cosmic history. Such regions might contain planets with similar geological evolution, similar atmospheric development, perhaps even similar biological processes if life represents a common outcome of planetary chemistry rather than an extraordinary accident. The scale of the unobservable universe makes such repetitions not just possible, but virtually inevitable if space extends sufficiently far. In a volume 10 to the power 90 larger than our observable universe, the number of possible arrangements of matter within galaxy-sized regions becomes finite, while the number of such regions becomes effectively infinite. somewhere in this vast expanse, cosmic evolution should have followed nearly identical pathways to our own. Yet the unobservable universe remains forever beyond direct investigation. No signal, no information, no physical influence can travel from these distant regions to our location. The fundamental speed limit of light, combined with the finite age of the universe, creates an absolute boundary beyond which observation becomes impossible, no matter how advanced our technology might become. This observational isolation means that the unobservable universe exists in a state of permanent disconnection from our cosmic neighborhood. Events occurring there right now will never influence anything within our observable domain. Similarly, nothing happening within our cosmic horizon can affect those distant regions. Each part of the larger universe evolves independently, connected only by the common physics that governs cosmic behavior everywhere. The cosmic expansion continuously pushes more regions beyond our observational reach. Galaxies currently visible at the edge of our cosmic horizon will eventually disappear from view as expansion carries them across the boundary between observable and unobservable space. Once they cross this divide, they become permanently isolated from our cosmic neighborhood, joining the vast population of galaxies that already exist beyond our horizon. This process operates in reverse as well. Our cosmic horizon expands outward at the speed of light, bringing previously unobservable regions into view for the first time. However, cosmic acceleration means that the rate at which galaxies disappear beyond our horizon exceeds the rate at which new regions become observable. The observable universe is gradually becoming lonelier as expansion isolates us from an ever greater fraction of cosmic space. The physics operating in the unobservable universe should be identical to what we study locally, but the outcomes of that physics might differ dramatically. Random quantum fluctuations during cosmic inflation would have produced different patterns of matter density in different regions. These variations would lead to different evolutionary paths, different distributions of galaxies, different frequencies of star formation, and different cosmic architectures. Some regions of the unobservable universe might have experienced different inflation histories, leading to cosmic domains with altered fundamental properties. If the strength of fundamental forces or the masses of elementary particles can vary across cosmic space, then distant unobservable regions might operate according to slightly different physical laws, creating cosmic environments unlike anything we can imagine. The anthropic principle suggests that we observe our particular cosmic neighborhood precisely because its properties allow for the existence of complex chemistry and biological evolution. Regions of the unobservable universe with different fundamental constants might remain sterile, lacking the delicate balance of forces required for stars to shine stably or for complex molecules to assemble into living systems. Dark matter and dark energy, the mysterious components that dominate cosmic evolution, presumably fill the unobservable universe just as they do our local cosmic neighborhood. These invisible substances should continue sculpting cosmic structure and driving expansion throughout the larger cosmos, creating the same kinds of dark matter scaffolding and cosmic acceleration that we detect within our observational domain. The unobservable universe challenges our understanding of scientific knowledge itself. Science traditionally relies on observation and experiment to test theories and validate models. But the vast majority of cosmic space lies beyond observational reach, accessible only through theoretical extrapolation, from the tiny fraction of the universe we can actually study. This situation resembles early geographical exploration, when mapmakers had detailed knowledge of local coastlines, but could only speculate about the contents of vast continental interiors. Just as those early explorers assumed that uncharted lands contained the same kinds of mountains, rivers and forests they observed locally, cosmologists assume that unobservable space contains the same kinds of galaxies, stars, and cosmic structures we detect nearby. The unobservable universe also serves as a reminder of cosmic humility. Everything we know about astronomy, every galaxy we've photographed, every star we've studied, every cosmic phenomenon we've discovered represents only the minutest sample of what actually exists. The universe in its full extent dwarfs our observable domain by factors so large that our cosmic neighborhood becomes essentially negligible in the grander scheme of existence. Future observations will continue to probe the relationship between our observable cosmic domain and the larger unobservable universe. Precision measurements of cosmic geometry might reveal whether space curves back on itself at scales larger than our current horizon. Studies of cosmic inflation might constrain how much larger the unobservable universe actually is compared to what we can see. The boundary between observable and unobservable space represents a permanent frontier, one that expands outward but can never be crossed by human exploration. Yet this boundary doesn't mark the edge of existence, merely the edge of accessibility. Beyond our cosmic horizon lies not emptiness or mystery, but more universe, more cosmic structure, more space filled with the ongoing processes of stellar birth and death, galactic evolution, and cosmic expansion that continue the story of existence far beyond the reach of our most powerful telescopes. Picture yourself as an ant crawling across the surface of a perfectly smooth sphere. You can walk in any direction, north, south, east, or west, and never encounter a barrier, cliff, or boundary of any kind. Yet the surface you're exploring is finite in area. This sphere has no edges, no borders, no points where the surface suddenly ends, yet it doesn't extend infinitely either. This strange combination of boundaryless finiteness offers a profound insight into how space-time itself might be structured at the largest cosmic scales. Einstein's general relativity revealed that space and time are not separate entities, but form a unified four-dimensional fabric called spacetime. This fabric can bend, stretch, and curve in response to matter and energy, creating the phenomena we experience as gravity. Just as our ant's spherical surface has intrinsic curvature that affects how geometry works on that surface, space-time itself has curvature that affects how physics operates throughout the cosmos. The question of whether space-time has edges becomes far more subtle than asking whether space has boundaries. In pre-relativistic thinking, space was imagined as a container, a three-dimensional box within which objects moved and events occurred. From this perspective, asking about spatial boundaries seemed natural. Either the box had walls marking its edges, or it extended infinitely in all directions. But relativity demolished the container metaphor. Space is not a stage upon which cosmic drama unfolds. Rather, space is part of the drama itself. Space-time participates dynamically in every physical process, curving around massive objects, stretching during cosmic expansion, even rippling with gravitational waves when black holes collide. This dynamic nature means that asking what lies beyond space-time becomes as nonsensical as asking what color Wednesday is, or what direction smells like happiness. Consider the geometry of our spherical ant's world more carefully. The surface has finite area, but no boundaries. If you tried to locate the edge of this surface, you would search forever without success. Every point on the sphere looks exactly like every other point from the ant's perspective. There's no special location where the surface terminates, no coordinate where the geometry suddenly breaks down. Space-time might possess similar properties. Our four-dimensional cosmic fabric could curve back on itself in ways that create finite volume without requiring boundaries. Just as the ant's two-dimensional surface wraps around to form a closed sphere, our four-dimensional space-time might close in on itself through higher dimensional curvature, creating what mathematicians call a hypersphere. In such a closed universe, space-time would have finite four-dimensional volume, but no edges or boundaries anywhere. A spaceship traveling in any direction through space would eventually return to its starting point, just as our ant circumnavigates the sphere. Time itself might even be closed, leading to cyclic cosmologies, where the universe repeats its history infinitely. The mathematics of general relativity allows for three fundamental types of space-time geometry, each with different implications for cosmic boundaries. Closed space-time curves back on itself like a sphere, creating finite volume without edges. Open space-time stretches infinitely like a saddle shape, extending forever in all directions. Flat space-time resembles ordinary Euclidean space, which can be either infinite like a plane or finite like a torus that wraps around on itself. Current observations suggest that our universe has nearly flat space-time geometry, at least within our observable region. This flatness extends across the entire cosmic horizon, implying that any curvature must be extremely subtle. But flat space-time doesn't resolve the boundary question. Flat space can be either infinite, extending forever without edges, or finite but wrapped, like the surface of a cylinder or torus. The topology of space-time, its connectivity and global structure, remains one of cosmology's deepest mysteries. Even if space appears flat locally, it could connect to itself in complex ways at larger scales. Imagine a piece of paper that appears perfectly flat from the perspective of an ant crawling on it. Yet this flat paper could be rolled into a cylinder, twisted into a Mobius strip, or folded into more complex shapes that change its global connectivity without affecting its local flatness. Space-time might possess exotic topologies that create shortcuts between distant regions. Wormholes, theoretical tunnels connecting different parts of the universe, would allow travel between distant locations without crossing the intervening space. Such connections would fundamentally alter the meaning of cosmic distances and boundaries, creating universes where remote regions link together through hidden geometric passages. The boundary question becomes even more complex when we consider the possibility of extra dimensions. String theory and other approaches to quantum gravity suggest that space-time might have more than the 4 dimensions we directly experience. These additional dimensions could be finite, even if the familiar 3 spatial dimensions extend infinitely. The universe might be bounded in some directions, but unbounded in others, creating hybrid geometries that defy simple classification. Quantum mechanics introduces further complications to the boundary question. At the smaller scales, quantum uncertainty might make the very concept of sharp boundaries meaningless. Space-time itself might fluctuate and foam at microscopic scales, with virtual black holes and wormholes spontaneously appearing and disappearing. In this quantum space-time, asking about precise edges becomes as problematic as asking about the exact position and velocity of an electron. The holographic principle emerging from black hole physics suggests that the information content of any region of space-time can be encoded on its boundary. This implies a deep connection between the interior of spatial regions and their surfaces, potentially making the distinction between inside and outside more subtle than classical physics suggests. If space-time is fundamentally holographic, then boundaries might not separate different regions, but rather represent different ways of describing the same underlying information. Loop quantum gravity, an alternative approach to quantum space-time, proposes that space consists of discrete units, tiny loops of geometry connected in a vast network. If space-time has this atomic structure, then asking about its boundaries becomes like asking about the edges of a crystal lattice. The boundary might not be a smooth surface, but rather a jagged frontier where the geometric network terminates. Causal structure provides another perspective on space-time boundaries. Every event in space-time has a past light cone, the region from which light signals could have reached that event, and a future light cone, the region that light from that event could eventually reach. These causal connections create a web of relationships that defines the structure of space-time itself. In a universe with space-time boundaries, causal structure would become incomplete. Events near the boundary would have truncated light cones, unable to receive signals from or send signals to certain regions. This incompleteness would violate the principle of causality that underlies much of modern physics, suggesting that truly bounded spacetime might be physically inconsistent. The cosmic microwave background offers tantalizing clues about spacetime geometry. The patterns of temperature fluctuations in this ancient radiation encode information about the curvature and topology of space when the universe was young. Subtle correlations between widely separated regions of the sky could reveal whether space wraps around on itself at scales larger than our current observable horizon. Future gravitational wave detectors might provide new insights into spacetime structure. These ripples in the fabric of spacetime itself carry information about the geometry through which they propagate. Gravitational waves that have traveled across significant fractions of the observable universe might reveal subtle signatures of cosmic topology or curvature. The question of space-time boundaries connects to fundamental issues in the philosophy of science. If space-time truly has no edges, then the universe becomes self-contained, requiring no external framework or container. This eliminates the need to explain what lies beyond the cosmic boundary, because no such boundary exists. Space-time defines its own arena, creating the stage for physics without requiring a larger theatre. Alternatively, if space-time does have boundaries, these boundaries must be described by physics beyond general relativity. Quantum gravity theories might predict how space-time terminates or connects to other structures. The boundaries themselves could be dynamic, evolving according to physical laws we don't yet understand. The absence of space-time boundaries would resolve many conceptual puzzles about cosmic edges. There would be no need to explain what exists beyond the universe, because beyond would have no meaning. No external space contains the cosmic boundary, because space-time itself defines the meaning of containment and location. String theory suggests that our four-dimensional spacetime might be embedded in higher dimensional spaces called the bulk. From this perspective, spacetime could have boundaries in the extra dimensions while remaining boundaryless in the familiar dimensions. The universe might be a four-dimensional membrane floating in a higher dimensional ocean, finite in some directions, but infinite in others. The search for space-time boundaries also involves examining cosmic singularities, points where the curvature of spacetime becomes infinite according to general relativity. The Big Bang represents such a singularity, a moment when the equations of general relativity break down completely. Some physicists wonder whether these singularities might represent true edges of space-time, boundaries beyond which physics simply doesn't apply. But quantum gravity theories suggest that singularities might not be fundamental features of space-time, but rather artifacts of our incomplete understanding. Loop quantum gravity predicts that the Big Bang singularity gets replaced by a quantum bounce, where a contracting universe transitions smoothly into an expanding one. String theory proposes that apparent singularities represent transitions between different phases of space-time geometry, like water turning to steam. The relationship between space-time boundaries and consciousness raises profound philosophical questions. Our minds evolved to navigate three-dimensional space with clear boundaries and edges. We instinctively think in terms of containers and contents, insides and outsides. When physics suggests that space-time itself might be boundaryless, we struggle to form mental images of such a reality. Consider how difficult it is to visualize four-dimensional space-time directly. We can understand it mathematically, describe it with equations, and make predictions about its behavior. But we cannot truly picture a four-dimensional hypersphere any more than a two-dimensional being could visualize a three-dimensional sphere. Our cognitive limitations might make space-time boundaries seem necessary, even when physics suggests they're impossible. The measurement problem in quantum mechanics adds another layer of complexity to space-time boundaries. Quantum states exist in superposition until they're measured, potentially allowing space-time itself to exist in superposed geometries. Before observation, the universe might simultaneously have boundaries and not have boundaries, with the act of cosmic observation somehow selecting one geometric reality from many possibilities. Modern cosmology has also revealed that space-time possesses an intrinsic arrow of time, a fundamental asymmetry between past and future. The universe began in a state of extremely low entropy and has been evolving toward higher entropy ever since. This thermodynamic arrow creates a temporal boundary, the Big Bang, even if spatial boundaries don't exist. The ultimate answer to whether space-time has edges might await a complete theory of quantum gravity. Such a theory would describe how space-time behaves at the smallest scales and under the most extreme conditions. It might reveal that space-time boundaries are impossible, that geometry necessarily closes in on itself, or that boundaries exist but connect to other spacetimes in a larger multiverse structure. Experimental tests of space-time geometry continue to push the boundaries of observational cosmology. Gravitational wave astronomy has opened new windows into the structure of space-time itself, allowing us to observe ripples in the cosmic fabric directly. Future space-based gravitational wave detectors might reveal subtle signatures of cosmic topology, or detect echoes that bounce around closed spatial dimensions. The cosmic microwave background remains our most powerful probe of primordial space-time geometry. Next-generation surveys will map temperature fluctuations with unprecedented precision, potentially revealing the statistical signatures of non-trivial topology. If space wraps around on itself at scales comparable to our observable horizon, these surveys might finally detect the cosmic Hall of Mirrors effect that would result. Advances in quantum field theory continue to refine our understanding of how matter and energy behave in curved spacetime. The Unruh effect predicts that accelerated observers experience thermal radiation even in empty space, suggesting deep connections between spacetime geometry and thermodynamics. The Hawking effect shows that black hole horizons emit thermal radiation, implying that boundaries in spacetime have intrinsic temperature and entropy. Current physics suggests that spacetime probably has no edges in the conventional sense. General relativity provides no mechanism for spacetime to simply terminate, and quantum mechanics makes sharp boundaries problematic. The fabric of spacetime appears to be either infinite in extent or finite, but wrapped back on itself, like our ant's spherical surface scaled up to 4 dimensions. Yet the possibility remains that spacetime boundaries exist in forms we haven't yet imagined. Perhaps boundaries represent transitions between different physical laws, rather than absolute terminations. Perhaps they connect our spacetime to other cosmic domains with different dimensionalities or physical constants. Perhaps they exist, but remain forever beyond observational reach, protected by fundamental limits on information transfer. This geometric insight transforms the boundary question from asking what lies beyond spacetime's edge to asking how spacetime curves and connects to itself. The universe might have no outside, because spacetime defines the very meaning of inside and outside. In this view, geometry itself eliminates the ancient question of cosmic boundaries by showing that such boundaries need not exist for spacetime to be well-defined and finite. The implications extend far beyond academic cosmology. If spacetime truly has no boundaries, then the universe becomes completely self-contained, requiring no external framework or transcendent realm. Everything that exists, has existed, or could exist finds its place within the curved geometry of spacetime itself. The cosmos becomes not just physically complete, but conceptually complete, answering its own deepest questions through the elegant mathematics of curved geometry. In the first tiny fraction of a second after the Big Bang, something extraordinary happened that would forever change our understanding of cosmic boundaries. During a period lasting less than 10 to the power minus 30 seconds, space itself expanded faster than ever before or since, stretching by a factor of at least 10 to the power 26 in an almost incomprehensibly brief moment. This epoch, called cosmic inflation, didn't just shape the universe we observe today, it potentially created a cosmos so vast that our entire observable universe represents merely one microscopic bubble in an infinite ocean of space. Cosmic inflation emerged as a solution to several puzzles that plagued Big Bang cosmology. The first was the horizon problem. Why does the cosmic microwave background have nearly identical temperatures in regions that should never have been in contact with each other? Without inflation, opposite sides of the sky correspond to regions that were separated by distances much larger than light could have traveled since the Big Bang. How could these causally disconnected regions have reached thermal equilibrium? The answer lies in inflation's dramatic expansion. Before inflation began, the region that would eventually become our observable universe was compressed into a volume smaller than a proton. At such tiny scales, all parts of this region were in intimate thermal contact, allowing temperatures to equalize completely. When inflation stretched this microscopic region to astronomical proportions, it preserved the thermal equilibrium across scales that became much larger than the cosmic horizon. The second puzzle was the flatness problem. Why does our universe have geometry so precisely balanced between closed and open? Current observations indicate that cosmic curvature is 0 to within about 1%, requiring incredible fine-tuning of initial conditions. Inflation solves this by stretching any initial curvature to enormous scales. Just as the surface of a balloon appears flatter as you inflate it to larger sizes, cosmic inflation stretched space-time until its curvature became negligible within our observable region. But inflation's most profound implication concerns the ultimate extent of space itself. Most models of cosmic inflation predict that the process doesn't end everywhere simultaneously. Instead, inflation stops in some regions while continuing in others, creating a fractal pattern of inflated domains separated by regions where expansion continues at exponential rates. This eternal inflation scenario suggests that space extends far beyond our inflated bubble, filled with countless other cosmic domains. Picture a pot of boiling water where bubbles form randomly throughout the liquid. Each bubble represents a region where inflation has ended, creating a universe with familiar physics and stable matter. But between these bubbles, the water continues to boil, representing regions where inflation persists, continuously stretching space and creating new volumes where additional bubbles can form. This analogy captures the essential idea of eternal inflation. Our universe is just one bubble in an infinitely bubbling cosmic ocean. Each bubble universe would have undergone its own period of inflation, ending at different times and potentially with different physical properties. The fundamental constants that govern physics, the masses of elementary particles, even the number of spatial dimensions might vary from bubble to bubble. Our cosmic domain would represent just one possible outcome among infinite variations on the theme of physical law. The landscape of string theory provides a theoretical framework for understanding how bubble universes might differ from each other. String theory predicts a vast number of possible vacuum states, each corresponding to different configurations of the extra dimensions that the theory requires. Estimates suggest there might be 10 to the power 500 different possible universes, each with its own unique combination of physical constants and natural laws. In this cosmic landscape, the properties we observe in our universe might not reflect fundamental necessity, but rather anthropic selection. We find ourselves in a bubble universe with physics that allows for stable atoms, long-lived stars, and complex chemistry, precisely because such conditions are required for observers like us to exist. Bubble universes with different physics might be sterile, unable to support the emergence of complexity and consciousness. The eternal inflation scenario creates a multiverse of staggering scope. If inflation is indeed eternal, then the total volume of space becomes infinite, filled with infinite numbers of bubble universes. Some of these bubbles would have physics nearly identical to ours, differing only in the random quantum fluctuations that seeded their cosmic structure. Others would have completely alien physics, with forces and particles unlike anything in our cosmic domain. Within this infinite multiverse, every possible outcome allowed by quantum mechanics would occur not just once, but infinitely many times. Somewhere in the vast expanse of bubble universes, there would be domains where matter arranged itself into configurations nearly identical to our cosmic neighborhood. The statistical arguments that suggest cosmic twins in an infinite universe become even more compelling in an eternally inflating multiverse. But the multiverse hypothesis raises profound questions about the nature of scientific explanation. Traditional science seeks to explain why our universe has the particular properties we observe. But if the multiverse contains universes with every possible combination of properties, then asking why our universe is special becomes like asking why a particular lottery ticket won. The answer might simply be that in an infinite collection of possibilities, every outcome occurs somewhere. This anthropic reasoning proves controversial among physicists. Some argue that multiverse theories are unscientific because they make no testable predictions about our observable universe. If anything is possible somewhere in the multiverse, then nothing is ruled out, and the theory becomes unfalsifiable. Others contend that multiverse models do make predictions about relative probabilities of different observations and could potentially be tested through their consequences. Cosmic inflation also predicts specific observational signatures that we can search for in our cosmic neighborhood. The rapid expansion should have stretched quantum fluctuations to macroscopic scales, creating the density variations that eventually became galaxies and cosmic structure. These primordial fluctuations should follow specific statistical patterns that depend on the details of the inflation process. The cosmic microwave background provides our best laboratory for testing inflation theories. The tiny temperature variations across the sky encode information about quantum fluctuations in the early universe. Different models of inflation predict different patterns of fluctuations, allowing observers to distinguish between competing theories by measuring the cosmic background radiation with sufficient precision. Gravitational waves from inflation represent another potential smoking gun. The rapid expansion should have created ripples in spacetime itself, primordial gravitational waves that would leave subtle imprints on the polarization of the cosmic microwave background. Detection of these B-mode polarization patterns would provide direct evidence for cosmic inflation and constrain the energy scale at which it occurred. The bubble collision signature offers perhaps the most direct way to test eternal inflation. If our cosmic domain collided with another bubble universe in the past, this collision should have left distinctive patterns in the cosmic microwave background. Several research groups have searched for such signatures, though none have been definitively detected so far. The physics of bubble formation during eternal inflation remains an active area of theoretical research. Different models predict different rates of bubble nucleation, different collision probabilities, and different distributions of physical constants across the multiverse. Some models suggest that bubble collisions should be common, while others predict that bubbles remain isolated from each other. The possibility of communication between bubble universes raises fascinating speculative questions. Could advanced civilizations in one bubble somehow signal to observers in neighboring bubbles? Might there be subtle channels for information transfer that we haven't yet discovered? Such communication would face enormous challenges, as the regions between bubbles continue to inflate exponentially, stretching any signals to undetectable wavelengths. Cosmic inflation also connects to fundamental questions about the arrow of time and the ultimate fate of the universe. In eternally inflating regions, the normal thermodynamic evolution toward higher entropy gets overwhelmed by the constant creation of new space. These regions might remain in a state of eternal youth, never reaching thermal equilibrium, continuously spawning new bubble universes throughout infinite future time. The measure problem represents one of the deepest challenges in eternal inflation theory. In an infinite multiverse, where every possible event occurs infinitely many times, how do we calculate probabilities? Standard probability theory breaks down when dealing with infinite sets, making it difficult to make predictions about what typical observers should expect to see. Various proposals have been made to resolve the measure problem, from cut-off prescriptions that artificially limit the multiverse to more sophisticated approaches based on the geometry of spacetime itself. The solution to this problem might determine whether eternal inflation makes testable predictions or remains forever in the realm of untestable speculation. The holographic principle adds another layer of complexity to multiverse theories. If the information content of any region can be encoded on its boundary, then the distinction between inside and outside a bubble universe becomes more subtle. The physics inside our bubble might be entirely determined by information encoded on our cosmic horizon, suggesting deep connections between our local physics and the larger multiverse structure. Quantum mechanics introduces additional complications through the measurement problem. In the multiverse, every quantum measurement produces different outcomes in different bubble universes. This raises questions about the nature of observation and consciousness in a cosmos where every possible outcome is realized somewhere. The eternal inflation scenario suggests that the question, what exists outside the universe, has a definitive answer: more universe. Beyond our cosmic bubble lies an infinite expanse of inflating space, filled with countless other bubbles, each containing its own cosmic domain with potentially different laws of physics. Our entire observable universe becomes just one room in an infinite cosmic mansion. Yet this answer comes with a price. If the multiverse truly contains infinite variations on physical law, then the specialness of our universe disappears. We inhabit just one of infinitely many possible cosmic domains, unremarkable except for the fact that its physics happens to allow for observers capable of asking questions about cosmic boundaries. The bubble universe picture transforms the edge question from asking what lies beyond a single cosmic boundary to asking about the structure of an infinite collection of cosmic domains. Instead of one universe with mysterious edges, we confront a multiverse with infinite extent but well-defined structure. The boundary of our cosmic bubble doesn't mark the edge of existence, but rather the transition from our familiar physics to the alien landscape of eternal inflation. This perspective suggests that cosmic boundaries might not mark the limits of reality, but rather the interfaces between different phases of cosmic evolution. Our bubble wall represents the boundary between the familiar matter-dominated universe we inhabit and the inflation-dominated regions that continue to expand exponentially beyond our cosmic horizon. The implications extend far beyond cosmology into philosophy, theology, and our understanding of humanity's place in existence. If eternal inflation is correct, then the cosmos becomes not just larger than we imagined, but infinitely larger, filled with infinite variations on the theme of cosmic evolution. The question of what lies beyond the edge of our universe receives a definitive answer that raises even deeper questions about the nature of infinity, existence, and our cosmic significance in an eternally creating multiverse. Horizons in physics represent far more than simple boundaries beyond which we cannot see. They are fundamental features of spacetime that encode information, process quantum mechanics in exotic ways, and challenge our deepest assumptions about the nature of reality itself. When we examine cosmic horizons through the lens of quantum mechanics and information theory, the question of what lies beyond the edge transforms from a geometric puzzle into a profound investigation of how information flows through the universe and what happens when that flow encounters absolute barriers. The most familiar horizon in physics surrounds every black hole, creating an event horizon beyond which nothing, not even light, can escape to the outside universe. For decades, Physicists treated this horizon as a simple geometric boundary, a point of no return where matter and energy disappear forever from the observable cosmos. But Stephen Hawking's revolutionary discovery in 1974 revealed that quantum mechanics transforms horizons into active dynamic boundaries that emit radiation and process information in remarkable ways. Hawking's insight emerged from applying quantum field theory near black hole horizons. In the quantum vacuum, particle-antiparticle pairs constantly appear and annihilate throughout seemingly empty space. Near a black hole's event horizon, these quantum fluctuations behave differently. Sometimes one member of a virtual pair falls across the horizon while its partner escapes to infinity. The escaping particle becomes real Hawking radiation, while the falling particle carries negative energy into the black hole, slowly reducing its mass. This process gives every black hole an effective temperature inversely proportional to its mass. Stellar mass black holes have temperatures of only billionths of a degree above absolute zero, making their Hawking radiation utterly negligible compared to other energy sources. But the principle remains profound. Horizons are not passive boundaries, but active quantum systems that thermalize information and emit thermal radiation. The cosmic horizon that surrounds our observable universe shares remarkable similarities with black hole event horizons. Just as we cannot receive signals from beyond a black hole's horizon, we cannot observe events occurring beyond our cosmic horizon. Both types of horizons represent causal boundaries where information flow becomes restricted, creating isolated regions of space-time that remain forever disconnected from our local physics. The Unruh effect provides another window into the quantum nature of horizons. An observer undergoing constant acceleration experiences thermal radiation even in apparently empty space, with a temperature proportional to their acceleration. This thermal bath emerges from the same quantum vacuum fluctuations that create Hawking radiation, but viewed from an accelerated reference frame rather than near a black hole horizon. The cosmic horizon creates a natural acceleration for distant observers. As cosmic expansion stretches space, galaxies near our horizon recede with ever-increasing speeds, approaching the speed of light asymptotically. From their perspective, they experience constant acceleration away from our location, suggesting they should observe thermal radiation associated with our cosmic horizon, just as accelerated observers detect Unruh radiation. This connection between cosmic expansion and thermal radiation hints at deep relationships between cosmology and thermodynamics. The cosmic horizon might possess an effective temperature and entropy, just like black hole horizons. If our cosmic boundary processes information thermally, then the question of what lies beyond becomes entangled with questions about information storage, processing, and the fundamental limits of computation in the universe. The holographic principle, discovered through studies of black hole thermodynamics, suggests that all the information contained within any volume of space can be encoded on its boundary. This principle emerged from the observation that black hole entropy scales with surface area rather than volume, implying that the maximum information content of any region is determined by its boundary area, measured in Planck units. Applied to cosmology, the holographic principle suggests that all the information within our observable universe could be encoded on our cosmic horizon. Every galaxy, every star, every quantum state within our cosmic domain might correspond to degrees of freedom living on the boundary of our observable region. From this perspective, the three-dimensional space we experience could be a holographic projection of information encoded on our two-dimensional cosmic horizon. The ADS-CFT correspondence, discovered in string theory, provides a concrete mathematical framework for understanding holographic duality. This correspondence establishes an exact equivalence between gravity in the interior of a curved spacetime and quantum field theory on its boundary. While the specific geometries studied in ADS-CFT don't match our actual universe, the principle suggests deep connections between bulk physics and boundary information. If our universe is holographic, then asking what lies beyond our cosmic horizon becomes equivalent to asking what lies beyond the degrees of freedom that encode our reality. The boundary might not separate us from additional space, but rather represent the fundamental information, theoretical limit of our cosmic domain. Beyond the horizon lies not more space, but simply the absence of the information degrees of freedom that define our local reality. Quantum entanglement adds another layer of complexity to horizon physics. When quantum systems become entangled, measuring one system instantly affects its partner, regardless of the distance separating them. This instantaneous correlation appears to violate the speed of light limit, but no information actually travels faster than light, because the correlations only become apparent when observers compare their measurement results through classical communication channels. Near horizons, quantum entanglement creates puzzles about information flow and causality. The black hole information paradox asks what happens to quantum information that falls across an event horizon. If black holes eventually evaporate completely through Hawking radiation, where does the information go? Quantum mechanics demands that information is conserved, yet general relativity suggests that information falling across horizons disappears forever. Similar puzzles arise at cosmic horizons. Quantum systems that become separated by cosmic expansion can remain entangled even after they cross our observational boundary. The entanglement persists, but we lose access to one member of each entangled pair as it recedes beyond our horizon. This creates a cosmic information paradox, analogous to the black hole case. How is quantum information conserved when expansion carries entangled systems beyond our causal reach? The ER equals EPR conjecture proposes a radical solution to these puzzles by suggesting that quantum entanglement and spacetime geometry are fundamentally equivalent. Einstein-Rosen bridges, theoretical wormholes connecting distant regions of spacetime, might be the geometric manifestation of Einstein-Podolsky-Rosen entanglement between quantum systems. If this conjecture is correct, then entanglement across cosmic horizons might create geometric connections that transcend apparent causal isolation. Quantum error correction provides another perspective on horizon information processing. Classical information can be lost when it crosses horizons, but quantum information might be preserved through natural error correction mechanisms built into the structure of spacetime itself. The cosmic horizon might function like a quantum computer, processing and preserving information even as classical signals become inaccessible. The firewall paradox illustrates how quantum mechanics can transform our understanding of horizon physics. Some calculations suggest that black hole horizons might be surrounded by walls of high-energy radiation that would incinerate any matter attempting to cross. If cosmic horizons possess similar firewalls, then the boundary of our observable universe might not be the smooth, empty space we imagine, but rather a violent interface where quantum effects create extreme physical conditions. Complementarity offers a potential resolution to these quantum horizon puzzles by suggesting that different observers can have equally valid but incompatible descriptions of the same physics. An observer falling across a black hole horizon experiences smooth, empty space, while an outside observer sees the information burned up in Hawking radiation. Both descriptions are correct within their respective reference frames, but they cannot be combined into a single global picture. Applied to cosmic horizons, complementarity suggests that observers in different cosmic domains might have fundamentally incompatible descriptions of the same physical reality. What appears as empty space beyond our horizon, from our perspective, might appear as active information processing from the perspective of observers in those distant regions. The boundary between domains might not have a unique physical description, but rather depend fundamentally on the observer's location and causal history. The emergence of space-time from entanglement represents one of the most radical proposals in modern physics. Instead of taking space-time as fundamental and studying how quantum fields behave within it, this approach suggests that space-time itself emerges from the entanglement structure of quantum information. Regions with high entanglement correspond to smooth space-time geometry, while disentangled regions correspond to disconnected or highly curved space-time. From this perspective, cosmic horizons might represent boundaries where the entanglement that creates space-time geometry becomes minimal. Beyond our horizon lies not additional space, but rather quantum information in a disentangled state that doesn't correspond to familiar geometric relationships. The edge of our universe becomes the edge of the entanglement pattern that weaves space-time itself. Quantum computational perspectives on cosmology suggest that the universe might be literally computing its own evolution, processing quantum information according to the laws of physics. Our cosmic horizon would then represent a computational boundary, the limit of the quantum calculation that defines our local reality. Beyond this boundary lies not more space, but simply the absence of the computational process that generates space-time and matter. The black hole complementarity principle might extend to cosmic horizons, suggesting that the information appearing to cross our boundary from our perspective remains accessible to observers in those distant regions. No information is actually lost, but different observer horizons create different perspectives on the same underlying quantum information processing system. Quantum field theory in curved space-time reveals additional subtleties about horizon physics. The very definition of particles depends on the observer's motion and the geometry of space-time. States that appear as empty vacuum to one observer can appear as thermal radiation to an accelerated observer or an observer near a horizon. This observer dependence suggests that the question of what lies beyond horizons might not have observer-independent answers. The cosmological constant problem connects to horizon physics through vacuum energy calculations. Quantum field theory predicts enormous vacuum energy densities that should curve space-time far more dramatically than observed. Some approaches to solving this problem invoke horizon effects that might regulate vacuum energy in ways that depend on causal boundaries and information accessibility. Emergent gravity theories propose that gravitational effects emerge from the statistical mechanics of quantum information near horizons. In these approaches, Einstein's equations become thermodynamic relationships describing how information flows across causal boundaries. The cosmic horizon becomes a thermodynamic system where information processing creates the appearance of gravitational attraction and cosmic expansion. The quantum nature of horizons suggests that cosmic boundaries represent informational rather than purely geometric phenomena. What lies beyond our cosmic edge might not be more space filled with matter and energy, but rather quantum information in states that don't correspond to the classical notions of space, time, and matter that define our local experience. This informational perspective transforms the edge question from asking about spatial extent to asking about the fundamental limits of information processing and quantum computation in the cosmos. Our cosmic domain represents the region where quantum information organizes itself into patterns we recognize as space-time, matter, and physical law. Beyond our horizon lies not absence, but rather the vast quantum computational substrate from which our familiar reality crystallizes through the mysterious process of cosmic information processing. Deep within the human psyche lies an ancient compulsion that shapes how we understand everything from our daily lives to the grandest cosmic mysteries. We are boundary seekers, edge finders, creatures who define ourselves and our world through the margins that separate one thing from another. This fundamental aspect of human cognition evolved over millions of years of navigating physical environments with clear spatial limits, now confronts us with the ultimate boundary question. What exists beyond the edge of everything itself? Our evolutionary heritage as spatial navigators runs so deep that it operates below the threshold of conscious thought. Every day we unconsciously calculate distances to walls, assess the boundaries of rooms, and define our personal space through invisible perimeters. Our brains contain specialized neural circuits for processing spatial boundaries, cells that fire specifically when we approach edges, corners, or transitions between different environments. These boundary detecting systems helped our ancestors survive by identifying safe territories, escape routes, and the edges of cliffs that could mean the difference between life and death. This biological legacy creates profound cognitive tensions when we attempt to comprehend a universe that might have no edges at all. Our minds rebel against the concept of boundaryless existence because such concepts violate the fundamental categories through which we organize experience. We instinctively ask what lies beyond any boundary, precisely because our neural architecture is designed to detect transitions between different spatial domains. Consider how children develop their understanding of space and boundaries. Even before they can walk, infants demonstrate awareness of spatial limits, reaching for objects within their grasp, while ignoring those beyond their reach. As they grow, children constantly test boundaries, physical and social, mapping the limits of their world through direct exploration. This boundary testing behavior reflects a deep cognitive drive to understand the structure of reality through its edges and transitions. Language itself reveals our boundary-obsessed nature. We describe experiences using spatial metaphors even when discussing abstract concepts. We speak of being on the edge of discovery, crossing the line between right and wrong, or pushing the boundaries of knowledge. These linguistic patterns reflect how thoroughly spatial thinking pervades human cognition, making it nearly impossible to think about existence without invoking concepts of containment, separation, and boundary. The concept of infinity presents particular challenges to human comprehension because it violates our evolved intuitions about spatial limits. We can manipulate infinite sets mathematically, reason about infinite sequences logically, and use infinity productively in scientific theories. Yet we cannot truly visualize or experientially grasp what infinite space would actually mean. Our minds keep trying to imagine infinite space as a very large container rather than accepting that infinity transcends all container metaphors. Religious and philosophical traditions throughout history have grappled with this tension between human boundary seeking and cosmic limitlessness. Many spiritual systems resolve the tension by placing the divine outside or beyond the physical universe, creating a transcendent realm that serves as the ultimate container for everything else. This satisfies our psychological need for boundaries by providing an external framework that encompasses all physical reality. Other traditions embrace paradox, teaching that ultimate reality transcends all categories, including the distinction between bounded and boundaryless. Zen Buddhism speaks of emptiness that is simultaneously full, while mystical traditions in many cultures describe experiences of consciousness that expand beyond all sense of spatial or temporal limits. These approaches acknowledge that our ordinary conceptual frameworks may be inadequate for grasping the deepest truths about existence. The scientific revolution confronted human boundary intuitions with increasingly counterintuitive discoveries about the nature of space and time. When Copernicus displaced Earth from the center of the universe, he violated our intuitive sense that we must inhabit a special, bounded location. When Newton described infinite space filled with stars, he challenged our assumptions about cosmic containers. When Einstein revealed that space and time form a unified fabric that can curve and stretch, he undermined our basic categories for understanding spatial relationships. Each scientific advance has required us to revise our intuitive picture of cosmic boundaries, yet our underlying cognitive drive to seek edges and limits remains unchanged. We continue to ask where the universe ends and what lies beyond, because our brains are wired to think in terms of spatial boundaries, even when physics suggests that such boundaries might not exist. The psychological impact of living in a potentially boundaryless universe varies dramatically among individuals. Some people find infinite space liberating, a cosmic arena large enough to contain all possibilities and dreams. Others experience cosmic anxiety, feeling lost or insignificant in a universe without edges or center. Still others respond with intellectual fascination, drawn to explore the mathematical and physical principles that govern boundaryless geometries. Cultural differences also shape how people respond to questions about cosmic boundaries. Societies with strong traditions of spatial exploration, from Polynesian navigators to Arctic peoples, often show greater comfort with vast, apparently limitless environments. Urban cultures accustomed to clearly defined boundaries may find boundaryless cosmologies more psychologically challenging. The anthropic principle offers one approach to resolving the tension between human boundary seeking and cosmic limitlessness. This principle suggests that we observe a universe with properties compatible with our existence, precisely because observers like us can only emerge in cosmic environments with appropriate characteristics. If the universe is infinite and contains regions with every possible combination of physical properties, then we naturally find ourselves in a region with physics that allows for complex chemistry and biological evolution. From this perspective, our boundary-seeking psychology is not a limitation that prevents us from understanding cosmic reality, but rather a necessary feature of any cognitive system that evolved in a universe capable of supporting observers. We seek boundaries because boundary detection was essential for the survival of the evolutionary lineages that led to us. The universe we observe appears comprehensible to boundary-seeking minds because only such minds could emerge within it. Yet, the anthropic principle raises its own philosophical puzzles. If we can only observe cosmic properties compatible with our existence, how can we determine which features of the universe reflect fundamental necessity versus anthropic selection? Our boundary-seeking psychology might prevent us from recognizing cosmic features that don't conform to our cognitive categories, creating systematic blind spots in our understanding of reality. The question of cosmic meaning becomes particularly acute when we consider the possibility that our entire observable universe represents an infinitesimally small fraction of a much larger multiverse. If eternal inflation has created infinite bubble universes with every possible combination of physical laws, then the properties we observe locally might not reflect any deeper significance, but merely anthropic chance. In such a scenario, our boundary-seeking questions lose their uniqueness. Every possible way of asking about cosmic edges occurs infinitely, many times throughout the multiverse, in bubble universes with observers whose cognitive evolution paralleled our own. The question of what lies beyond the edge becomes simultaneously universal and meaningless, asked by infinite observers in infinite cosmic domains. Some philosophers argue that infinite multiverse scenarios eliminate all meaning and significance by making everything equally actual. If every possible story unfolds somewhere in the multiverse, then no particular story, including our own, possesses special significance. Others contend that meaning emerges locally within each cosmic domain, regardless of what happens elsewhere in the larger multiverse. The simulation hypothesis adds another layer to questions about cosmic boundaries and human meaning. If our reality represents a computational simulation running within some larger substrate, then the boundaries of our universe might correspond to the limits of the computational system that generates our experience. What lies beyond the edge could be simply the hardware and software that implements our simulated reality. This possibility transforms boundary questions from physics into computer science. Instead of asking about the geometry of spacetime, we might need to ask about the architecture of cosmic computation. The edge of our universe could represent memory limitations, processing boundaries, or the interfaces between different computational systems. Consciousness itself presents the ultimate boundary question for human understanding. We experience the universe from within our conscious awareness, but the relationship between consciousness and physical reality remains deeply mysterious. The hard problem of consciousness asks how subjective experience emerges from objective physical processes, a question that bears striking similarities to asking how the universe emerges from whatever lies beyond its boundaries. Some approaches to consciousness suggest that awareness is fundamental to reality, not something that emerges from purely physical processes. If consciousness plays a fundamental role in the structure of the universe, then questions about cosmic boundaries might be inseparable from questions about the limits and nature of conscious experience itself. The existential implications of boundaryless space challenge many traditional sources of meaning and significance. If the universe extends infinitely in all directions, containing infinite variations on every possible theme, then individual choices and actions might seem to lose their cosmic importance. Why does anything matter if everything that could possibly happen does happen somewhere in infinite space? Yet infinity might also offer new sources of meaning. In a boundaryless universe, there are no fundamental limits on possibility, no ultimate constraints on what conscious beings might achieve or become. The absence of cosmic edges could represent the absence of cosmic limitations, opening infinite frontiers for exploration, creativity, and growth. The question of whether the universe has boundaries ultimately reflects deeper questions about the nature of existence, consciousness, and meaning. Our boundary-seeking psychology, evolved for navigating finite spatial environments, confronts cosmic possibilities that transcend all familiar categories. Whether we find this confrontation liberating or terrifying depends partly on our individual psychology and partly on the cultural frameworks we use to interpret our place in the cosmos. Perhaps the most profound insight from our exploration of cosmic boundaries is the recognition that the question itself reflects something fundamental about human nature. We ask about edges and limits, not just because we want to understand the universe, but because boundary seeking is central to how our minds organize experience. The cosmic edge question represents the ultimate expression of our cognitive drive to map reality through its boundaries and transitions. The universe may or may not have edges, but our questioning certainly reveals edges in human understanding. We bump up against the limits of our evolved cognitive categories, the boundaries of our conceptual frameworks, the edges of our ability to visualize and comprehend. In seeking the boundaries of the cosmos, we discover the boundaries of human thought itself. This recognition might transform how we approach cosmic boundary questions. Instead of seeking definitive answers about what lies beyond the edge, we might focus on understanding why we ask such questions and what our asking reveals about the relationship between mind and cosmos. The edge question becomes not just a puzzle about cosmic geography, but a window into the deepest connections between consciousness, cognition, and the structure of reality itself. The human need for boundaries, confronted with the possibility of boundaryless existence, creates a tension that drives both scientific investigation and philosophical reflection. This tension might never be fully resolved, but exploring it deepens our understanding of both cosmic reality and human nature. In the end, the question of what lies beyond the edge of the universe becomes inseparable from the question of what lies at the heart of human consciousness and its eternal quest to understand its place in the vast cosmic arena that contains and defines our existence. We have journeyed from ancient mythologies that imagined crystalline spheres containing the cosmos to cutting-edge theories of quantum information and eternal inflation. We have explored every scientific approach to the ultimate boundary question, examined the philosophical implications of infinite space, and confronted the psychological roots of our edge-seeking nature. Now, as we reach the end of our exploration, a remarkable conclusion emerges from the convergence of multiple lines of evidence. The universe, in all likelihood, has no edge in any conventional sense of the word. This conclusion represents one of the most profound reversals in human thinking about cosmic reality. For thousands of years, across cultures and civilizations, humans assumed that everything must have boundaries. Rooms have walls, countries have borders, oceans have shores, and surely the universe itself must have some ultimate edge, where existence meets non-existence. Yet modern physics suggests that this fundamental intuition, so deeply embedded in human cognition, simply doesn't apply to the cosmos as a whole. General relativity provides no mechanism for spacetime to terminate abruptly. Einstein's equations describe how matter and energy curve the fabric of space and time, but they contain no provisions for that fabric to suddenly end at some cosmic boundary. Space can curve back on itself like the surface of a sphere, creating finite volume without edges. It can stretch infinitely like a flat plane or saddle shape, extending forever in all directions. But it cannot simply stop, because there is no physical principle that would cause such termination. The expanding universe initially seemed to suggest cosmic boundaries. If space is growing, surely it must be growing into something, expanding beyond its previous limits into new territory. But this intuition reflects our container metaphor for space. The mistaken idea that space is like a box that can grow larger within some external framework. Cosmic expansion doesn't represent space growing into external territory, but rather the creation of new space itself, the stretching of the cosmic fabric from within. Cosmic inflation, the period of rapid expansion in the universe's first instant, potentially stretched space to infinite size, regardless of whether it began finite or infinite. Even if the primordial universe started as a microscopic region smaller than a proton, inflation could have expanded it to infinite extent, eliminating any possibility of edges or boundaries. The observable universe we inhabit today would represent just one tiny patch of this infinite expanse. The cosmic microwave background, our deepest view into the primordial universe, shows no evidence for boundaries or edges. The temperature patterns across the sky appear statistically uniform in all directions, suggesting that space continues beyond our observational horizon with the same properties we observe locally. If our cosmic domain were approaching a boundary, we might expect to see asymmetries or special directions in the cosmic background radiation, but no such features have been detected. Quantum mechanics eliminates the possibility of sharp, well-defined boundaries at the microscopic scale. Quantum uncertainty makes precise edges impossible, replacing them with fuzzy transition regions where properties change gradually rather than abruptly. If spacetime itself has quantum properties, as suggested by theories of quantum gravity, then cosmic boundaries would be fundamentally impossible because quantum systems cannot have perfectly sharp edges. The holographic principle suggests that apparent boundaries might not represent true separations between different regions, but rather different ways of describing the same underlying information. If our observable universe is holographic, encoded on our cosmic horizon, then asking what lies beyond that boundary becomes like asking what lies beyond the information that defines our reality. The boundary doesn't separate us from external space, but rather represents the informational limits of our cosmic domain. Dark energy, the mysterious force driving cosmic acceleration, provides additional evidence against cosmic boundaries. This energy density appears uniform throughout space, showing no signs of approaching edges or limits. If dark energy continues beyond our observational horizon with the same properties, it would drive eternal expansion of infinite space rather than pushing space against cosmic boundaries. String theory and other approaches to quantum gravity suggest that spacetime might emerge from more fundamental structures that naturally avoid boundary problems. If space and time are not fundamental but rather arise from the collective behavior of more basic entities, then questions about cosmic boundaries become questions about the underlying substrate from which space-time crystallizes. This substrate might be infinite in extent, or have topological properties that eliminate boundary issues. The multiverse scenarios emerging from eternal inflation transform the boundary question by suggesting that our entire observable universe is just one bubble in an infinite collection of cosmic domains. What lies beyond our cosmic edge isn't emptiness or mystery, but more universe, other bubble domains with potentially different physical laws floating in an eternally expanding substrate. The boundary of our cosmic bubble doesn't mark the edge of existence, but rather the interface between our local physics and the larger multiverse structure. Yet even as current science points toward a boundaryless universe, important caveats remain. Our observations are necessarily limited to our cosmic horizon, roughly 46 billion light-years in radius. Beyond this boundary, direct observation becomes impossible, leaving us to extrapolate from local evidence. It remains conceivable that space has properties beyond our horizon that differ dramatically from what we observe locally. Quantum gravity theories, still under development, might reveal new physics that allows for cosmic boundaries in ways we haven't yet imagined. The unification of quantum mechanics and general relativity could produce effects that become important only at cosmic scales or in extreme conditions, potentially creating boundary phenomena beyond our current theoretical understanding. The possibility of extra dimensions adds complexity to boundary questions. While our familiar 3 spatial dimensions might extend infinitely, additional dimensions predicted by string theory could be finite and bounded. The universe might be infinite in some directions, but finite in others, creating hybrid geometries that challenge simple classifications of bounded versus boundaryless space. Future observations will continue to test our understanding of cosmic structure and boundaries. Next-generation telescopes will probe deeper into space and further back in time, potentially revealing new evidence about cosmic geometry and topology. Gravitational wave astronomy opens new windows into the structure of space-time itself, offering possibilities for detecting subtle signatures of cosmic boundaries or confirming their absence. Precision measurements of cosmic geometry will determine whether space is exactly flat or possesses slight curvature that becomes apparent only on scales larger than our current horizon. If space curves back on itself, we might inhabit a finite but boundaryless universe, like the 3-dimensional analog of a sphere's surface. If space is exactly flat, it could be either infinite or finite, with complex topology that wraps around on itself. The cosmic microwave background will be mapped with ever greater precision, potentially revealing subtle correlations that indicate non-trivial topology. If space wraps around on itself at scales comparable to our observable horizon, future surveys might detect the cosmic Hall of Mirrors effect that would result from seeing the same structures from multiple directions. Advances in fundamental physics might resolve deep questions about the nature of space, time, and information that bear on cosmic boundary issues. The development of quantum gravity could reveal whether space-time is truly fundamental or emerges from more basic structures. The resolution of the black hole information paradox might illuminate how information flows across cosmic horizons and what happens at the boundaries of causal domains. The philosophical implications of a boundaryless universe continue to challenge human understanding. If space truly extends infinitely in all directions, then every possible arrangement of matter occurs not just once, but infinitely many times across the cosmic expanse. This includes perfect duplicates of our solar system, our planet, and ourselves, living out identical or slightly varied versions of our lives in distant cosmic regions. The statistical mechanics of infinite space create paradoxes that challenge our concepts of probability and meaning. In an infinite universe, every event that can happen does happen infinitely often, making it difficult to assign meaningful probabilities to cosmic phenomena. The rare becomes common when multiplied by infinity, and the impossible becomes inevitable given sufficient space and time. These implications extend beyond physics into questions about identity, consciousness, and free will. If infinite space contains infinite copies of our brains, with identical thoughts and memories? What makes our particular instance of consciousness special? Do all these copies share the same identity, or are they separate beings who happen to have identical experiences? Such questions push the boundaries of philosophy as well as physics. The absence of cosmic boundaries also eliminates certain theological and metaphysical problems while creating others. If the universe is self-contained and boundaryless, it requires no external creator or sustainer, no transcendent realm that contains physical reality. The cosmos becomes completely self-sufficient, answering its own questions about existence through the elegant mathematics of curved geometry. This self-containment challenges traditional cosmological arguments for divine existence that depend on the universe requiring an external cause or container. If space-time needs no external framework, then arguments from cosmic contingency lose their force. The universe becomes not a created object requiring explanation, but the fundamental framework within which all explanations have meaning. Yet this same self-sufficiency might be interpreted as pointing toward deeper mysteries. Why does mathematical law govern physical reality? Why do the fundamental constants have values that permit complex structures and conscious observers? Why does anything exist at all rather than nothing? A boundaryless universe answers the question of cosmic containment, but amplifies questions about cosmic fine-tuning and the unreasonable effectiveness of mathematics in describing natural phenomena. Boundaryless infinity might seem to diminish human significance by making our cosmic neighborhood infinitesimally small compared to the whole. In infinite space, our entire observable universe becomes negligible, our galaxy becomes invisible, our solar system becomes undetectable, and human civilization becomes utterly insignificant from a cosmic perspective. The Copernican revolution displaced Earth from the center of the universe, but infinite space eliminates the concept of cosmic center entirely. This cosmic humbling extends beyond mere scale to questions of uniqueness and specialness. If infinite space contains infinite variations on every possible theme, then nothing we do or discover can be truly unprecedented. Every human achievement, every work of art, every scientific breakthrough, every moment of love or creativity occurs infinite times throughout the boundaryless expanse. Our personal histories become infinitely repeated cosmic themes rather than unique biographical narratives. The mathematical concept of measure theory attempts to assign meaningful probabilities to events in infinite spaces, but these technical solutions often feel unsatisfying when applied to questions of human significance. Knowing that infinite copies of ourselves exist throughout boundaryless space challenges our intuitive sense of personal identity and individual importance. Alternatively, the absence of boundaries might enhance rather than diminish human meaning. In a boundaryless universe, there are no fundamental limits on what consciousness might achieve or become. No cosmic edges constrain the expansion of knowledge, creativity, or ethical development. The universe offers infinite frontiers for exploration and infinite possibilities for growth and transformation. Infinite space means that conscious beings have unlimited room for expansion, both literally and metaphorically. Civilizations could spread across vast cosmic regions without ever encountering ultimate boundaries. Knowledge could grow without limit because new phenomena would always exist beyond current understanding. Creativity could explore infinite variations on artistic and cultural themes. Love and ethical development could extend across unlimited communities of conscious beings. The absence of cosmic boundaries also means that consciousness faces no ultimate constraints on its evolution. In a finite universe, there would eventually be limits on complexity, information processing, and the scope of possible experience. But boundaryless space offers unlimited resources for the development of increasingly sophisticated forms of awareness and understanding. Some philosophers argue that infinite space makes individual consciousness more rather than less significant because each conscious perspective represents a unique window into infinite reality. No two observers, even infinite copies of the same being, can have identical experiences because they occupy different locations in the infinite expanse. Each consciousness becomes an irreplaceable viewpoint on the totality of existence. The eternal return concept from philosophy takes on new meaning in infinite space. If every possible event occurs infinite times, then in some sense, every moment becomes eternal. Every experience becomes endlessly repeated. Every choice becomes infinitely significant because it occurs infinite times throughout the cosmos. This might enhance rather than diminish the meaning of individual actions by making them permanent features of cosmic reality. The anthropic principle suggests that we observe cosmic properties compatible with consciousness, not because the universe was designed for us, but because only such properties allow observers to exist. In infinite space with varying physical properties, observers naturally find themselves in regions conducive to their existence. This selection effect means that the apparent fine-tuning of our cosmic neighborhood reflects observational bias rather than cosmic specialness. Yet anthropic reasoning creates its own puzzles about the nature of observation and existence. If infinite space contains observers in every possible situation, then the anthropic principle becomes circular. We observe what we observe because we can observe it. This tautological character makes anthropic explanations feel unsatisfying, even when they might be technically correct. The many worlds interpretation of quantum mechanics resonates with boundaryless cosmology by suggesting that all possible quantum outcomes are equally real. In infinite space, these quantum possibilities might be spatially separated rather than existing in parallel dimensions. Every quantum measurement that could yield different results does yield different results in different cosmic regions. The quantum multiverse becomes a spatial multiverse spread across boundaryless space. This spatial distribution of quantum possibilities eliminates the need for parallel universes or additional dimensions. All possible quantum histories unfold in different regions of infinite space, making the entire quantum landscape simultaneously real and spatially accessible, at least in principle. The boundaries between quantum possibilities become spatial separations between cosmic regions rather than barriers between different reality layers. The edge question that began our journey has led us to recognize that edges themselves might be artifacts of limited perspective rather than fundamental features of reality. Just as Earth appears flat from a local perspective, but reveals its spherical geometry from a global view, the universe might appear bounded from our limited horizon, while actually being boundaryless when viewed from a more complete perspective. This recognition transforms our understanding of what it means to ask about cosmic boundaries. The question, what lies beyond the edge of the universe, might be similar to asking, what lies north of the North Pole, or what color is the number 7? These questions seem meaningful until we recognize that they rest on category errors, misunderstandings about the nature of the entities they purport to describe. If space-time defines the very meaning of location and extension, then asking what lies beyond space-time becomes as nonsensical as asking what exists outside of existence itself. The universe might have no edge because the concept of edge requires a boundary between something and something else. But if the universe encompasses everything that exists, there is no something else to serve as the other side of the boundary. The scientific journey toward understanding cosmic boundaries has revealed as much about the nature of human cognition as about the structure of the cosmos. Our edge-seeking psychology, evolved for navigating finite environments with clear spatial limits, encounters phenomena that transcend all familiar categories. The resulting cognitive tension drives both scientific investigation and philosophical reflection. We discover that the universe challenges our deepest intuitions about space, time, and existence. the cosmos appears to be far stranger than our evolved psychology prepared us to comprehend. Infinite space, curved geometry, quantum uncertainty, and holographic information storage violate the common sense categories through which we typically organize experience. Yet this strangeness might be precisely what we should expect. The universe is under no obligation to conform to human cognitive categories or to satisfy our psychological need for familiar spatial relationships. The fact that cosmic reality transcends our intuitive understanding might reflect the profound depth and complexity of existence rather than any failure of human reasoning. As we conclude our exploration of cosmic boundaries, we find ourselves not with definitive answers, but with transformed questions. Instead of asking what lies beyond the edge of the universe, we might ask why we assume there must be an edge at all. Instead of seeking the location of cosmic boundaries, we might explore the boundaries of human understanding itself. The greatest discovery in our journey is not the location of the cosmic edge, but the recognition that the edge we sought might not exist. The universe, in its vast complexity and profound depth, appears to be structured in ways that transcend the boundary concepts that seem so fundamental to human thinking. At the universe's edge, we do not find a wall or barrier or transition to something else. Instead, we find the limits of our imagination and the beginning of a deeper appreciation for the remarkable strangeness of existence itself. The cosmos reveals itself not as a container with edges, but as the very definition of spatial reality, not as an object with boundaries, but as the framework within which all boundaries have meaning. In seeking the universe's edge, we discover that the universe is not contained within space, but rather contains space, not limited by boundaries, but rather the source from which all limits derive their significance. The cosmos reveals itself not as a container with edges, but as the very definition of spatial reality, not as an object with boundaries, but as the framework within which all boundaries have meaning. In seeking the universe's edge, we discover that the universe is not contained within space, but rather contains space, not limited by boundaries, but rather the source from which all limits derive their significance. This reversal represents a fundamental shift in human cosmic understanding, comparable to the Copernican revolution or the discovery of quantum mechanics. Just as these earlier revolutions required abandoning intuitive but incorrect ideas about planetary motion and physical determinism, recognizing the universe's boundaryless nature requires abandoning our intuitive but possibly incorrect assumptions about cosmic containment and spatial limits. The practical implications of this shift extend beyond academic cosmology into how we think about exploration, discovery, and humanity's cosmic future. If space truly extends infinitely, then the notion of cosmic frontiers becomes more subtle. We cannot explore the universe's edge because no such edge exists, but we can explore ever larger scales and ever more distant regions, each revealing new phenomena and deeper principles. The technological implications are profound as well. In a bounded universe, there would eventually be limits on expansion, resource acquisition, and the scope of possible engineering projects. But boundaryless space offers unlimited room for growth, unlimited resources distributed across infinite scales, and unlimited possibilities for technological development that works with rather than against cosmic structure. The educational implications challenge how we teach cosmology and spatial reasoning. Traditional pedagogy often begins with familiar bounded objects like rooms and buildings before gradually expanding to larger scales. But if the ultimate cosmic reality is boundaryless, then perhaps education should emphasize the mathematical and conceptual tools needed to think coherently about infinite systems from early stages. The psychological implications vary greatly among individuals and cultures. Some people find the concept of boundaryless space liberating and inspiring, a cosmic arena vast enough to contain all dreams and possibilities. Others experience anxiety or existential vertigo when contemplating infinite extension, feeling lost in a cosmos without landmarks or ultimate destinations. The artistic and cultural implications create new challenges and opportunities for creative expression. How do we create meaningful art about boundaryless space? How do we tell stories set in infinite cosmos? How do we develop cultural traditions that help humans find meaning and purpose in a universe without edges? These questions represent new frontiers for human creativity and cultural evolution. The scientific implications continue to unfold as observational cosmology and theoretical physics develop new tools for studying cosmic structure. Even if direct observation beyond our horizon remains impossible, future theories might make testable predictions about the properties of unobservable space. Quantum gravity, unified field theories, and advances in mathematical cosmology could provide new insights into the fundamental nature of spatial infinity. This reversal of perspective, from seeking external boundaries to recognizing internal completeness, represents perhaps the most profound shift in human cosmic understanding since we first looked up at the night sky and wondered where it all ends. The answer we find is both humbling and magnificent. It doesn't end at all, and we are not separate from it, but woven into its very fabric, participants in an ongoing cosmic story that has no final chapter because it is written on pages that extend beyond all horizons, in a book whose covers encompass everything that was, is, or ever could be. Yet even as we embrace this boundaryless vision, we must remain humble about the limits of current knowledge. Our understanding of cosmic structure depends on extrapolating from observations within our limited horizon to make claims about the infinite expanse beyond. Future discoveries might reveal cosmic features that challenge our current picture of boundaryless space. The development of quantum gravity theories might uncover new physics that operates only at cosmic scales, potentially creating boundary phenomena beyond our current imagination. The unification of all fundamental forces could reveal hidden relationships between space-time geometry and particle physics that affect cosmic structure in ways we haven't yet anticipated. Advanced civilizations, if they exist in our cosmic neighborhood or beyond, might have developed observational techniques that transcend our current limitations. Their knowledge of cosmic structure could dwarf our understanding just as our current cosmology dwarfs the astronomical knowledge of ancient civilizations. Contact with such beings might revolutionize our understanding of cosmic boundaries and spatial infinity. The possibility remains that consciousness itself plays a fundamental role in determining cosmic structure. If awareness and observation are necessary components of physical reality, rather than mere byproducts of complex chemistry, then the distribution of conscious beings throughout space might affect the global properties of the cosmos in ways we don't yet understand. These uncertainties remind us that scientific knowledge remains provisional, subject to revision as new evidence emerges and new theoretical frameworks develop. The boundaryless universe represents our best current understanding based on available evidence, but science progresses by questioning even its most successful theories and remaining open to unexpected discoveries. Nevertheless, the convergence of multiple independent lines of evidence toward a boundaryless cosmos is remarkable. General relativity's prohibition of spatial termination, quantum mechanics' elimination of sharp boundaries, cosmic inflation's prediction of infinite space, observational evidence for flat geometry, and the absence of detected boundary signatures all point in the same direction. This convergence suggests that the boundaryless universe is not merely a theoretical possibility, but the most likely description of cosmic reality. While future discoveries might modify or refine this picture, they would need to overcome substantial evidential momentum that currently favors infinite, edge-free space.